Hello everyone, welcome back to Dragonfly Engineering. So this week we are going to mold these Microgroove chips, and you can see there's three little grooves in the chip that connect to a snout at the top, which is a through hole. And these chips are about 1 square inch. And these were actually shown molding in last episode in the molding machine, so I made this mold about a month ago. And this is the batch of parts, it's probably 1,000 parts in there. But on the CAD model here, you can see more details of the device. There's a couple of alignment holes in the front, and then the snouts here at the back. And these snouts are going to be created using some core pins, which will also act as ejector pins. So you can see where I highlight here with the yellow crescent, or the orange crescent. That is where the ejector pin and the other side of the mold will connect. And then I'm going to turn on the mold block. So in SolidWorks we can create the mold using the mold features, and then this is the assembly of the two mold halves that were created. And again, in that hole, or that feature, that cylinder at the top, that is actually going to have a ejector pin pierce through it, which I didn't completely model this mold because it's kind of a quick job. And here's the molding machine running the mold, so you kind of get a sneak preview here. So let's go ahead and start the process of making this. I'm in the shop with several of the HAAS mills running at 10,000 RPM. So the shop is pretty noisy. So a lot of this beginning information and throughout this video is going to be this voiceover. So here you can see how I've tapped in the aluminum mold block. This is 7075 aluminum. And we're facing off the top with the round insert shell mill. This is a 3-inch shell mill. And then, this is kind of what you do with every start of a mold, is you get a nice clean surface. And then with the probe here, I'm going to find the center of the mold. And then after that, I'll switch back to regular audio. Okay, we're going to use this 40 thousandths or 1 millimeter end mill to profile their little flow channels in our plastic part. And basically we're going to raster cut for several hours this tiny tool back and forth on the surface of the mold, and that will 3D kind of subtractive cut or subtractive print the profile of the mold into the surface, ideally with a flat mirror-like finish. So we'll go ahead and tighten this guy. So I'm going to let this guy just sit here and spin at 10,000 RPM for probably half an hour. And what we're doing is we're accumulating the heat in the spindle so that when we actually do start to cut, the spindle has stopped growing from heat, from the high RPM of the spindle spinning. So there we're up at 10,000 RPM. I bring the tool down to the surface. This is a spindle chiller, which is on the side of the machine, which cycles cooling oil through the spindle and through this chiller to help control the temperature of the spindle. And even with that chiller running, I still need to run the spindle to hit a temperature equilibrium so we don't see errors in the surface of our mold surface. So here I'm just heating up the spindle with running it at 10,000 RPM for about 30 minutes or so. And now I'm setting the tool height after the spindle has heated up and reached equilibrium. Okay, so we're back with the zoom lens here. Let's zoom in on this action. Here we go. So now we're going to be machining our micro flow channel surface into this aluminum block. Let me hit the air burst so you can see the shape forming. There it is. And we got about 3 hours of this to go. So we'll do some time lapse, even though you may not be able to see much. All right, so there is our machine surface. It looks like there's a little bit of a temperature wave in there, but I bet I can polish that out. So while the mill is hot and everything is set on its particular thermal growth, we're going to go ahead and machine the 2 alignment pin bearing holes for this mill. Because as things cool off, then positions can change a little bit. So to maximize accuracy, we'll go ahead and cut those bearings in now. So let me go ahead and stop this program. Then we'll move that tool to the spindle. Oh, and that's a roughing end mill, but it's probably going to be okay. Now the height of this tool is not critical, but its XY position is important. It is a 4-flute radius tip roughing end mill, but I think we'll be fine with that. So I'm just going to eyeball the height of this tool. Because there's slop in the depth for these bearings that we're going to press in. And then tool setup, set length. Then we'll raise off. And the sooner we cut this, from the time that we cut the high precision mold cavity, the more accurate our position of the 2 mold halves are going to be. So I will go ahead and hit start. I've got the rapid reduced, and I'm going to have my finger on the hold stop. Okay, so now we'll go ahead and machine in our bearing holes. Hopefully there's not too much splash. And this is a 5/8 inch or 22.2 millimeter hole for our linear plane sleeve bearings that I'll press into this mold. I might babysit it to make sure it doesn't bog down the tool, because it is a 4-flute cutting in aluminum. And I can speed up the rapid. Getting a little splash out, so I'll close one door. There we go. See if I can zoom in on it for you. Oh, you know what? I hope I have enough exposure on this tool. Might be a little tight. I don't think I'm going to make it. Yeah, I better interrupt. All right, so I'm going to switch this tool out because I think it'll get, basically my collet holder is going to get too close to the mold surface. So let me switch out to a longer tool. I'll be right back. All right, so we got a longer end mill. And I'm going to reset the tool height. This is definitely long enough. And I'm going to eyeball the height again because it's not a critical dimension. There we go. There, that definitely gave us more room. Okay, let's run that again. And I can speed it up to get past or get down to the actual height. All right, so I got you zoomed in on the mold cavity that we machined yesterday and last night. Apologies, but I went ahead and did a flatness check by polishing one of the bays on this mold surface, so you can kind of see the reflection here. So this line right here is the one that I polished. But you can see just right off the mill from the milling swirl marks, it doesn't look super flat and polished. You know, you see kind of these swirl marks in it. But if you come along with some polish, this is like a cerium oxide based metal polish. And if we polish up this surface a little bit, this is just a Q-tip with some store-bought metal polish from McMaster-Carr. I can show you the type or the brand here in a second. But with a real quick polish using just a Q-tip and some of this cerium oxide, I can demonstrate how flat and smooth the surface is. So this is basically what I did last night. I needed to decide if I was going to recut this surface or not, and I decided that it was good enough so that we didn't have to remachine. But you can see the resultant finish from essentially just doing that very small raster cut, going back and forth with like a 3,000 step over. The accumulation of basically all the swirl marks from the end mill tips and just the sheer number of cut passes results in a polishing of the surface. So, and it doesn't really reveal until you hit it with literally like 10 seconds of a cerium oxide metal polish. So like if we do this bay next, then basically I'm just getting rid of the optical effect from sub-micron swirls from the cutting tip. And then if I come over here and this is a dry swab, which probably isn't a good idea on aluminum. So let me hit this with some, I have lacquer thinner because I can't get isopropyl alcohol anywhere. So anyway, let's clean this surface off. I probably do need to get another swab. I'll just dab it here with the paper towel. But yeah, that's how our surface is cleaning up. Let me get that. Kind of do a general wipe of all of that. So that's what our surface looks like. Let me get the old Sharpie marker so you can get a reflective reference. Anyway, so I'm pretty happy with that finish actually. So you can machine mirror finishes with these mills because of their micron accuracy that you can get these days. So yeah, not too bad. The other thing that you want to do is the lower the observation angle to the surface of the mold, the more ripple you can see in the surface. So there is a slight ripple. So now we're moving over to the HAAS TM1 Mill, which is next to the Herco that's making the other mold half. And we are going to start on the B side of the mold. And this is the one that has those holes that are going to be 3D machined in and ultimately drilled through for the formed ejector pins. So we're setting this guy up, and then we're going to do the same tapping in and the same facing of the top of the mold off, and then I will come back to you with real audio. Look at this number right here. When I turn the spindle on, this line right here is spindle load. And with the spindle off, it's 0% and 0.0 kilowatts of power being drawn for the spindle. But when I turn it on to 4,000 RPM, you'll see how it went up to 6.5 kilowatts to spin up the RPM on the spindle, just the momentum of the mass of the spindle. But now that we're running at 4,000 RPM, the spindle is consuming 100 watts of power, 0.1 kilowatts, which is about 3% to 4% of the spindle load, just to keep its RPM going from the friction and resistance of it spinning at that high of an RPM. So if I reduce the RPM down to like 200, you'll watch the spindle load change. So now we're running at 199 RPM, and you can see the spindle load is 1% or barely reading. So running at a low RPM, the spindle cools off, but when we go back to 4,000 RPM, you'll see that we're sitting here running at 100 watts. And that means that 100 watts of electricity is turning into 100 watts of heat in the spindle. So what we need to do is let the spindle heat up so it reaches equilibrium with the room, and then it won't change its temperature, and thus it won't change its length, and which means that the end mill will not change its depth of cut into the mold cavity itself. Okay, now that we got the spindle warming up at 4,000 RPM, I'm going to go ahead and set the tool height. So I'm using this optical loop like I've done before, and I'm looking at how basically the gap between the tool and the reflection of the tool in the aluminum goes to 0. And it's a visual inspection of that gap. When I get close, I'll start to spin the tool, looking for first contact or the first little chip. Okay, so our tool height is set and the 0 is set, but I'm going to double check the 0 location. Under the MDI, I'm going to tell it to go to X0, Y0 and cycle start. And that is our 0 location. So now I'm going to go ahead and hit run after I reduce the feed rate and the rapid rate, just for safety. And menu and cycle start. Okay, we are good. I'm going to run coolant on this. So the coolant temperature should be the same as the aluminum block because it's sitting in the same room. But this spindle, I don't really spray coolant on it because it's a slower RPM spindle, and a lot of the spindle bearing is up inside of the housing of the mill. So there we go. Our second mold half is cutting, and we will just let it go for a while. I'll probably set up a time lapse for you. Okay, so I came back, it's about 9 o'clock at night, to see how this milling operation is going, and it must have just finished because there's still liquid on top of the mold. So let's do a reveal of our surface. And this is a good opportunity for me to go ahead and machine in the alignment pin holes on this mold as well, because we're still at temperature. So X and Y should still be basically within a few microns of where it was when we actually machined this cavity. So I am going to take the opportunity tonight to machine in these 2 alignment pin holes, and then probably see how the mold surface looks in the morning. But yeah, this kind of time is of the essence for temperature control. So let's go ahead and pull this guy up. We'll use probably a 1/4 inch end mill. Let's see if I got one loaded. I'll have to find one. All right, so I will write the program for the alignment pins real quick, and we'll be right back. We just need to have a pocket deep enough to contain the 1/2 inch dowel pin that we are going to press into this mold. So I'm going to eyeball the tool depths. I decided to do a drill as well. That's in position 4. I'm not sure what this drill diameter is, but it's basically just a clearance hole to make the 3D machining of the pocket for the pins a little easier. It's just hogging out the excess stock in the middle of the hole. Okay, there we go. So I will load the program and we will cut our dowel pin alignment holes. Okay, here we go. You'll notice it's a lot quieter because the other two mills that were running at high RPM are finished with their programs for the day. So I can actually talk a little more reasonable. Okay, so I will 5% rapid, 100% feed and spindle, and hit cycle start. And this will set our locations. We'll do a little cooling as well. And again, I'm only doing this step tonight because the mill just stopped and it's at temperature. So this is the best probability of getting good alignment on the two mold halves. We don't need to do the drill operation, so what I'm going to do is go to menu, and I can scroll down through the program, and this is instructions for drilling, and then you see this 2.5 axis pocketing. That's what we want to replay with the 1/4 inch end mill. So if we highlight this line, then what's going to happen is the mill is going to skip all of the other steps and go straight to this line to do the 2.5 axis pocketing for the finish hole for the dowel pins. But with the HAAS, it does some kind of strange things. It'll actually change tools back to the previous tool. So I'm going to go ahead and hit cycle start with the line highlighted halfway through the program. You can see how the mill is actually changing tools, even though it's changing out the tool that it's going to use. So it goes to the drill, and then it's going to actually come down and peck the drill, and then come back up, not even actually touch the stock. And it's this thing with HAAS where it loads the previous tool, and then goes back and loads the same tool that it's about to run, and then reruns the program from where we started it in the program on the controller. And then you can see back on the screen here how it's basically just cycling through that helical 3D data. Let me get you focused on it. Yeah, so anyway, it's a funny thing with HAAS. When you start a program halfway through, it goes through this sequence. Now I can tell you with the HERCO mills, if I start a program halfway through and it didn't see the spindle start command, then it will actually try to pick up and start running the program with the spindle not spinning, which would crash the tool. So I guess a credit to the HAAS controller, it goes through a sequence to make sure that wherever you start in the program, at least the right tool is in there and the spindle is on, where that's not the case with the HERCOs. So every mill package has its pluses and minuses. You can see we're basically running the same program over again. And all those chips that are forming is basically aluminum that remained because the end mill was flexing too much. This end mill isn't super sharp. So a lot of times it's good to run a program twice just to clean up the tool flex and the material that you missed because of the flexure of the tool is bending out of the way instead of cutting. Let me center that a little better. Yeah, so all of that is lost material, or remaining material because the tool was flexing on the first cut. So I'll bet the dowel pin will fit now. Yeah, that was a lot of material left behind. And again, this is an identical program, so it should be, if this tool didn't flex at all, then there should be no chips left. But yeah, there's a decent amount of chips there. All right, let's try our dowel pin. Then I'm going home. All right, so I'm gonna load a second 3R combi chuck. It's a work holding chuck on this mill. And the combi chuck is used for holding electrodes for the EDM process. And I'll show you briefly how this works. But basically this is the 3R combi chuck, not sponsored, but I just needed to buy another one to expand the mold making and EDM aspect of the shop here. But essentially this structure holds down a plate, and on that plate you bolt your your electrode that you're ultimately going to load into the EDM machine behind us. And then you pull down the plate with this screw right here. So there's a collet holder, a collet clamp inside of there, and it draws a collet down that's on the plate. And then when that plate comes down, it references these structures and perfectly aligns the plate in X, Y, Z and A, B, and C axes. So it's completely defined. So I've already stoned this surface, and I'm going to, and oil, put some whey lube on there just to prevent any rust. I'm going to let this guy sink in. Probably got to level my mill. Have a nice oil bearing there currently. But anyway, so we'll just scrub this out, and that oil will get thinner and thinner. And we're ensuring that we're not going to let any water get in there. And these surfaces are both very flat, so it could take, well, theoretically forever to get all the oil out. But when we clamp it down, that'll definitely help. Okay, and then I got some small strap clamps here. And this clamp has, or this chuck has a couple of clamping schemes. You can also mount this chuck 90 degrees, which actually I bought 2 of these, and I'm going to do that on the other mill. But now I got 2 mills that can cut electrodes, because right now I'm getting backed up on basically mold making because of lack of electrode machining stations. I will also have to indicate this chuck in. There's a special indicating tool that we load onto the chuck here in a second. So I got to make sure that indicating is going to go reasonably well as well. So what you do is you load this reference edge and position into the combi chuck using one of these pull studs here. And so basically you flip the guy over, you put the pull stud in, you spin it, and then you push down on this little plastic retainer. And then this piece is contained by the pull stud. Now the pull stud remains loose. So then what we do is we just drop this guy on to the 3R combi chuck. Combi means combination because it actually holds 2 types of work holding. Yeah, my handle is going to interfere with my strap clamp here. I'm kind of on the edge of the table, so I'll have to move these 2 vices over so I get better positioning. Anyway, so when I tighten that screw, now this piece of work, which currently is an alignment tool, is positioned perfectly and repeatably. So now what we're going to do is I'm going to get the indicator out, and we're going to indicate in this edge and then knock this chuck into square on the mill. Okay, we're a little closer now. Let's bring our indicator back. See how good I am at visually aligning. Let me get the little rubber mallet. Okay, so now what I'm doing is I'm checking, or I'm aligning, or I'm finding the center of this reference geometry to find the center of the 3R combi chuck down here. So I've done some of the grunt work already, and I'm just going to dial in the final position. So I basically got the probe down inside of the hole, and we'll set the left side to 0. We'll swing this guy around. And then on this side we've got a 5, so I'm going to move the spindle by 2.5 thousandths. I'll reset to 0. And then when I swing to the back, we're at minus 1 thousandths. Again, I've done a lot of the busy work of finding close to the center. I didn't want to bore you with whole lot of just fuss. But there we're at 0, there we're at half a thousandths, there we're at 0, and here we're plus half a thousand. So let me dial in Y a little better. You probably can't see this dial, so sorry about that. But basically I'm spinning this indicator around, and when the needle doesn't move anymore and it's in contact, so I can wiggle the needle, that means I've found the center of this combi chuck. So the whole idea with this chuck is the same chuck is on the spindle of the EDM machine, so whatever I machine on this chuck and the plate that will go onto this chuck will be centered on the EDM machine in the same way. So it's a nice way to swap work back and forth between two machines. Okay, I think we're good. So I will set the X and Y position, and we are ready to start cutting the EDM electrode that is going to burn the little profile in the top of our ejector pin core pin for this mold, for this guy. Okay, so I'm drilling and tapping the mounting holes on the back of this copper electrode blank, which is like a 3/4 inch shaft of copper. And we're going to do the tapping now. And then this piece of copper will screw in to the bottom of the smaller of the two types of chucks that the 3R work holding system uses. It's called a combi chuck because it either holds these bigger plates that are like 2 inches square, or it holds a center axial smaller referencing plate or puck, if you will. And we're going to use the smaller center puck and screw this block of, or this cylinder of copper right into the smaller puck. So I'll show you that in a second as soon as we're done tapping this guy. These are 632 threads. It's got a weird like 3 screw geometry on it, which is a little tricky to figure out because it's actually rotated off axis. But anyway, let's see how we do about fitting this guy into the 3R smaller chuck. Alright, so there's our... Alright, so this is the little puck that I was telling you about. This is our copper blank, and basically what we're doing is we're going to mount the copper onto our puck, and then this puck is going to be loaded into the 3R tool holding or work holding chuck that we just put on the mill over there, and then we can essentially machine our electrode shape into the top of this copper when this puck is perfectly centered on that chuck, so we don't have to indicate this guy in. And then when we're done machining our electrode shape, then we will load this system onto the EDM machine and start burning the profile into our hard steel pins. So that is the sequence of events. I think I've got the collet here. Oh, sorry for, there we go. Make sure we're tight. I don't want to over tighten and break the little ball off of this thing. Okay, let me get the pull stud. Okay, here's our puck that we just screwed onto place, and then here's the pull stud that screws into this puck here. So basically we just spin this guy on. It has like a O-ring down the center if we wanted to have coolant go through, or EDM oil go through the center, but we're not going to mess with that. And there we go. This is our pull stud and stock that we're going to load into that chuck that we just centered on the mill to machine our EDM profile that we're then going to burn the same profile into the tips of our hard steel pins. So I'll meet you over at the mill. Okay, we're over at the mill, and yeah, you basically just put the pull stud in there. You find where the 3 splines match with the 3 spokes in the surface of this combi chuck, and push it down. Whoops. And then we draw the pull stud down into the chuck with this screw here, and there's something that's grabbing the pull stud and seating and pulling this part. I really should have not put this that strap clamp right there, but anyway, so let me tighten this guy down. And there you go, the copper is positioned exactly correctly, and now I can machine the profile into the tip of this guy. This looks like a good spot to conclude the video for this week, but please stay tuned next week and you can see the conclusion of the mold fabrication that we're doing, as well as loading the mold onto the molding machine and molding the parts. I'd also like to thank my new patrons on Patreon for supporting this channel. I'll put a list of the patrons at the end of this episode. And if you like the information that you're receiving through these videos on machining and mold making, then please consider being a patron yourself by going to Patreon and looking up Dragonfly Engineering. And also, please like and subscribe the video if you want to see more as well. And I always enjoy comments in the section, or the comment section. And with that, I will see you all next week. Please enjoy the final preview for next week's episode. Thank you for watching.